Hi, I'm Vishwas, and I'll be talking about learning generalized depth-3 circuits in the non-degenerate case. This is joint work with Ankit Garg, Neeraj Kayal, and Chandan Saha. Let me start by quickly defining arithmetic circuits. Arithmetic circuits are directly acyclic graph where every internal node is addition or a multiplication gates. Leaves are input gates where you can have a constant from the field or a variable, and every edge gets a label from the underlying field. Let's see how computation happen in arithmetic circuit. Here, you start with the leaves and you go bottom up, and whenever you see a gate, you look at all the things which go into the gate and apply the operation corresponding to them. There are few parameters associated with the circuit. There's the size of the circuit, which is the number of gates, depth of the circuit, which is the depth of the directed acyclic graph, and you can, without loss of generality, assume that your circuit is layered. That is, there is a layer of multiplication gate followed by a layer of addition gates and so on and so forth. And for instance, this circuit is depth 3 sigma by sigma circuit because of this layering. And this is an example of how computation happen in arithmetic circuits. There are three fundamental problems related to arithmetic circuits. One is lower bound, in which you have to find an explicit polynomial which is not computable by small circuits in your class. Other is polynomial identity testing, in which you're given a circuit either directly or as a black box access in which you can evaluate it at any point you like. And the aim is to compute or test if that polynomial computes a zero polynomial or not. And the third problem, learning, also known as reconstruction, which is the main focus of this talk. Here, you're given a black box access to a polynomial, and your aim is to come up with a small circuit computing that polynomial. There are several connections known among these problems. Let's look at the few. There are connections between lower bounds and PITs. These are known as hardness randomness trade-offs, in which you can get lower bounds from PIT and PIT from lower. There are other connections in which there's connection between lower bounds and learning algorithms. Here, for example, there's a result by Fortman Clevans, which gives you lower bounds if you have a learning algorithm. And also, there have been few learning algorithms which are inspired from the lower bound techniques. In this talk, we'll look at a new meta connection which was put forward by Kayal Saha and further worked on by Garg, Kayal, and Saha. Here, they say that if you have a lower bound for a circuit class C, you can use that lower bound to get non-degenerate learning for the circuit class C. So let me elaborate on the asterisks here. So the asterisk here means that you get lower bound via a technique in which you look at a vector space corresponding to the circuit and you analyze its dimension. And what Kayal and Saha are saying, that if your lower bounds come via this, we can look at that vector space and try to learn from that lower bound technique. Note that, as you pointed out before, the other direction already exists. The other direction, in fact, exists formally, in which if you have reconstruction algorithm for C, that will give you a super polynomial lower bound for the circuit C with some level of explicitness, a BPEXP polynomial. Now, one might wonder, why are we getting non-degenerate learning instead of general learning for the class C? And what does it mean to have a non-degenerate learning? So we say, let's answer that question by looking at what is degenerate input. So we allow our algorithms to fail at certain inputs, and those we call it degenerate inputs. Those inputs are of the form that there is some algebraic dependence or algebraic relations among intermediate gates of the circuit, which we don't hope that most circuits have. And those circuits we call degenerate. And we want to say that we can learn all the circuits except barring a few, which if you sample from any reasonable distribution will not be. So also, why do we need this non-degenerate condition is because we know some special models for which we have lower bounds, but if we also get learning for them, that will violate the NP hardness of them. So they are NP hard to learn them, So there should be some inputs on which we should fail. So that's why we need some kind of non-degeneracy condition. So let's look at an example in which it's a very famous known algorithm, and let's look at it from the lens of tensor decomposition. I'm sorry, of non-degenerate learning. So this is the problem of tensor decomposition, symmetric tensor decomposition effect, in which you are given a polynomial f, and you have to write it as sums of cubes of linear polynomials. This is known to be worst case NP hard, and there is an algorithm due to Henrix, which if S is less than n and all the LIs are linearly independent, then you can recover this LIs. That is, you can learn the circuit. Now, if you think of this as a non-degenerate learning algorithm, what's the non-degenerate condition? The non-degenerate condition is that LIs are linearly independent. And also note that here the number of summonds you can handle is closely linked to the best known lower bound. So this known algorithm fits into the framework of non-degenerate learning. Now, before moving on, let's do a quick survey of what's known in learning. So first thing to know about learning is it's expected to be a really hard problem for most circuit classes. We have some evidence that points us to that there's NP hardness results which show that some circuits, if you learn them, that's NP hard. There's also that learning imply lower bounds, which we struggle with. And then there is analogy to MCSP, which is considered a really hard problem in Boolean setting. And there's also some cryptographic hardness results now. Despite all these hardness results, there has been substantial progress for learning algorithms for arithmetic circuits. We can classify those into worst case learning and average case learning. In worst case learning, we put extreme restrictions on the circuit. For instance, the top finite is constant, or they're just sparse polynomials, things like that. While in average case learning, we assume that our circuit is nice structured, and we put some extra constraint on them. So they are not worst case, but they can handle much bigger circuit classes. So let's look at what we know for worst case. We can learn sparse polynomials, ROAVPs, and depth 3 and depth 4 circuits, assuming the top finite is bounded. There are quite a bunch of technical conditions which I'm glossing over just to give the overall picture. But again, we need top finite bounded conditions, or we need sparse polynomials, things like that. For average case, we either need, for instance, we need the formulas. We can learn formulas in the average case, but we need that it should be top finite 2 regular multilinear formulas or general formulas. So we need this extra condition. Or we can learn constant width branching programs, assuming some extra conditions. So recently, there is focus on non-degenerate learning, where we don't put structural requirement on the circuit, but we just assume that there is no non-trivial dependence among intermediate gates, and that's non-degenerate learning. And there has been work by Kayal and Saha for depth 3 circuits, and by Garg, Kayal, and Saha for sums of powers of low degree polynomials on this. And we further build on non-degenerate learning in this work by giving a learning algorithm for generalized depth 3 circuit in this work. So let's talk about a meta framework. So suppose I give you a polynomial and I want to write it as sum of TIs, where TIs are some simple polynomials. So the main idea of Kayal and Saha is that non-degenerate learning for F, that is writing F in this form, reduces to vector space decomposition of vector space linked with F, such that if you can decompose that vector space as direct sums, that direct sum, those vector spaces, will give you information about Ti itself. So that's the main idea of Kayal and Saha, is to reduce learning to a question of vector space decomposition. So let's see how we can do that. To do that, we need some linear operators that act on your polynomial ring up to some degree D. So for instance, we look at the kth order partial derivative operators. Now if you apply this operator set of operators L on your polynomial f, which is summation ti, you get the following relation. You get that L of f, this vector space, is contained in some of these vector spaces. So, but we want some kind of direct sum to use our vector space decomposition kind of setting. So for that, we assume and we hope that the non-degenerate setting, we have the following thing: that first, that we have direct sum structures among addition of these vector spaces, and an equality instead of inclusion here, and we point it as a non-degenerate condition 1. That is, if you apply linear operators on your polynomial f, you get this direct sum structure and an equality among vector spaces. Note that such decomposition might not be unique, uh, because there are lots of ways of decomposing a vector space as direct sum of smaller vector spaces. So to make it unique, so that we can extract the information of TIs from them, we have to do something else. So to do that, we, instead of looking at a set of linear operators, we look at linear operators which is composition of two linear operators. For example, if you look at k plus 1th order partial derivatives, that's can be thought of as composition of kth order partial derivative with first order partial derivative. So now we have the following. We have a vector space, let's call it U, and you can write it as a direct sum of UIs. UIs are when you apply L1 on TI. And similarly, you have V, which is L of F, and you have VIs, which is L of TIs. And you can go from U to V and UI to VI when you apply L2 on these vector spaces respectively. So this is what we refer to as vector space decomposition problem for this talk. For example, let me give a concrete definition. So if I give you a set of linear operators from vector space U to V, and your aim is to decompose U as a direct sum, V as a direct sum, such that L sends UI to VI for all I in S, and further UI and VI are further indecomposable. Note that the setting we have after applying linear operators satisfy this. It's just a special case of vector space decomposition problem. And as it turns out, if there's something called adjoint algebra of L, U, and V, this tuple, if that's trivial, then we also get uniqueness, which we were looking for. So let's quickly look into what adjoint algebra means. We won't go into too much detail, but just showing you the definition. So adjoint algebra for a tuple L, U, and V, where L is a set of maps that maps vector space U to vector space V, is are tuples which are linear maps D and E, which says U to U and V to V, such that L of D and E is equal to E of L for all linear operators in the set L. And we say that this adjoint algebra, it's easier to check that this is in fact an algebra. Uh, we say that this algebra is trivial if the restriction to the subspaces Ui and Vi are identity up to scalar multiplication, which means that if you restrict D to Ui, that's equal to lambda I identity, and if you look at restriction of E to Vi, that's again identity up to some scalar multiplication for all I in S. So it's easy to check that these trivial maps will always be in the adjoint algebra, and when we say our adjoint algebra is trivial, we mean there's nothing in the adjoint algebra apart from. So that's the adjoint condition. That will be our third condition. So we assume, so that is the second non-degenerate condition, right? The first we assume direct sum structure and equality, and the third would be the adjoint algebra is trivial, right? And if we assume that condition, then we get uniqueness of decomposition, and not only that, we get something else. So that's a vector space decomposition problem again. And there are results by Chistov, Karpinski, and Evanus. And also we get a self-contained algorithm in our work that there exists a polynomial time algorithm which solves this exact vector space decomposition problem, assuming that the adjoint algebra is trivial. So if you have adjoint condition with you, then you can solve this vector space decomposition problem. All right, so let me summarize the meta framework here. So you're given a polynomial f, and your aim is to write a sum of some simple polynomial ti's. To do that, you use some linear operators and look at the space u and v. U is the vector space that you get after applying L1 on f, and v is the vector space that you get by applying L to f. And by non-degeneracy condition 1, you get this direct sum structures. And if the adjoint of L2, U, and V is trivial, that we assume is our non-degeneracy condition 2, then there exists an efficient algorithm that outputs the unique decomposition. So basically, that's how our learning algorithm go. For if you want to learn a model in which we have to write a polynomial f as sum of some simple polynomials, we smartly come up with some kind of linear operators in composition form, and we look at our vector space decomposition problem that arises naturally from them, and we hope that the non-degeneracy 1 and 2 will be satisfied. And if that's the case, we can use our vector space decomposition algorithm to get our hands on these vector spaces, and hope to use these vector spaces to learn TIs. So let's see our meta framework in action using our favorite example, which is sums of cubes or linear forms. So here our linear operators would be second order partial derivatives, and you can use these operators to prove lower bounds for this model, and note that they are also compositions of first order partial derivatives. So we have the following diagram. So our non-degenerate condition to learn this model would be Li's being linearly independent, and if Li's are linearly independent, you get that L1 of f, which is a vector space U, is in fact a direct sum. Why? Because if Li's are linearly independent, then so are Li squares. And even if you apply L2 on top of that, you get span of Li's. And again, because Li's are linearly independent, you get that there is direct sum structure here as well. So the next thing we have to show is that adjoint is trivial. So it's an easy exercise to show that if Li's are linearly independent, then the adjoint for these maps will also be trivial. We won't be discussing here today, but it's an easy exercise. So we can get Yenrik's algorithm, which we discussed before, by just using our template and using the non-degeneracy condition being Li's being linearly independent. So this is how we can use our template for sums of powers of linear forms, or here sums of cubes of linear forms. So now we'll focus on the rest of the talk in about our model. That's the work we did for here we do learning for generalized depth circuits. A generalized depth circuit is an expression of the following kind, in which your simple polynomial, so you have a sum of two simple polynomials, and a simple polynomial is a polynomial of arity m, so it's a low arity polynomial, relatively low in the sense, and you can feed arbitrary linear forms into that polynomial, into the low arity polynomial. So your generalized depth circuit looks like that. So the parameters involved here are S, which is the number of is the number of some summons, GI, which is an m variable polynomial of homogeneous degree D, and Li's are linear forms in n variables. So that will represent a generalized depth 3 NSDM circuit. Note that this subsumes the depth 3 circuit when GIs are just monomials. A technical side note that we should really call them homogeneous generalized depth circuit, because we are looking at GIs being homogeneous and Li's being homogeneous, but we will just refer to them as generalized here for simplicity. And the result that we show that we can learn the generalized depth 3 circuit in the non-degenerate case, assuming that n is greater than md square. This essentially means the arity is bounded by square root n by d, and the number of summons is bounded by n to the d by 4, and the character is 0 or large enough. So again, as we said before, we should first show lower bounds before going into learning. So So what's the lower bound for this model? Actually, the vanilla partial derivative operators just work fine to give lower bounds for this model. So we look at linear operators in kth order partial derivative space, and it's easy to check that these individual vector spaces, that is L being applied on Ti, is bounded by m plus k minus 1 choose k. Why? Because these are essentially k variate polynomials of degree d, and if you apply partial derivative on them, your space will be bounded by m plus k minus 1 choose k. And by the subadditive property, we'll get that the dimension of L composed of U, that is dimension of a vector space that we get after applying the operator L on F, is bounded by this. And it's easy to come with a polynomial with very high dimension. That is, you think of, let's say, elementary symmetric polynomial, something like that. And you get a high dimension polynomial, and by the straightforward techniques we get that S is lower bounded by n by m to the k, and your m is like square root n, so that will give you a lower bound directly. So again, to conclude, we can get lower bounds for this model by just using partial derivative operators. Now the question is, can we use partial derivative operators and the vector space generated by them to get learning as well? And the answer is yes, and that's what we do in this work. So again, we look at k plus 1th order partial derivative space, and these are composition of first order partial derivative for and kth order partial derivative, and that's a vector space decomposition problem. And we'll be having this direct sum structure due to non-degenerate conditions. And then we can apply our vector space decomposition algorithm, assuming that the adjoint is trivial. So let's look at the complete picture now, because we are not given these vector spaces to begin with. We are just given black box access to F. But using black box access to F, it is easy to get black box access to the kth order partial derivatives of F in nd to the k time, and k will be small for us. Using that, we can get partial derivative access to this vector space, let's call it U, and similarly to this vector space V. So we can feed that into a vector space decomposition algorithm, and we'll have these conditions due to non-degenerate condition 1 and 2. And using that, we can get access. The output of the vector space decomposition algorithm would be the space partial derivative uh, operator k applied to Ti's. And we can use the Lagrange formula to get Ti's out of this. So that's the complete picture. Here, you can use black box access to F, a vector space decomposition algorithm, and Lagrange formulas to get black box access to individual TIs. That's the complete algorithm. But we are hiding the main thing, which is why would the non-degenerate condition hold? And that we'll discuss now. We'll show why these non-degenerate condition will hold for random circuits or most circuits. So let's look at one condition, which is direct sum property. So this is how our polynomial looks like, and we have that Lij's are, let's say, random. We are not putting any assumption on Gi's right now, and we have to show that these vector spaces, which is the sum of these vector spaces, is actually a direct sum. And we instead show that, since we are not assuming anything on Gi's, we show that the polynomial ring up to degree d minus k that we get by having Lij's, this comes from Ti's, those form direct sum. And since these UIs are contained in this bigger vector space, showing that they form direct sum directly imply that these things form direct sum. And let's discuss briefly how we show that this is the case. So this showing that this direct sum property boils down to showing some kind of linear independence of some polynomials, which you can show that some big polynomials whose coefficients are these linear forms Lij's is non-zero. It will be some determinant. And so if you can show that that polynomial is non-zero by giving a particular evaluation point on which the polynomial is non-zero, then by Schwarzschild lemma, even for random Li's, this will be non-zero. So we just have to show that equation 1 holds for a fixed set of LIs. And we construct that set LIs of LIs using Nissan-Wigderson design family. So these are the conditions that we get from the design family, which also come up in our main theorem. And you can imagine that if these are disjoint set of linear forms, if you look at the vector spaces, the monomials they generate, since the intersection of this design family is limited, cannot cancel one another. So there will be a direct sum structure, there will be linearly independent. For adjoint condition 2, note that we have to use GI because uh, they depend. There exists GIs in which the adjoint is non-trivial, even if you choose LIs randomly. So here we show that if you choose GIs randomly, or GIs are some interesting polynomial families that we care about, like determinant, permanent, monomials. For all those cases, the adjoint is in fact trivial, and that's the main result we show. We show that if you have a generalized depth circuits under this constraint, and if you choose LIs to be randomly, and your GIs comes from these set of polynomial families, determinant, permanent, iterative matrix multiplication, and symmetric polynomials, then your circle is non-degenerate. Or if you choose your coefficients of GIs randomly, even then your circuit will be non-degenerate with high probability. And a direct corollary of this and our algorithm is that we can learn random generalized circuits assuming these condition hold. To conclude, we showed that we discussed the meta reduction that reduces learning to vector space decomposition. We used our reduction to show that we can learn non-degenerate and in fact random generalized circuit. And we leave the following problem as open, which is implementing this template for other models where we know lower bounds. For example, constant depth multilinear circuits. Thank you.